we showed you how to find basis for a row space of a matrix. You basically take the matrix and apply elementary row operation, and then you write it in row echelon form. The number of non-zero vectors basically is the answer to the basis for the row space of the matrix. The number of non-zero row vectors is 3 in this case. So these 3 vectors form a basis for the row space of A. Now I expect you to ask, what if we want to find the basis for the column space of the matrix? We're going to apply this method to find the basis for the column space of matrix A. Just need to find the basis for the row space of the transpose of A. Very good. It's not that difficult. So first, you're going to write down the transpose of the matrix and then apply elementary row operation to write the transpose in row echelon form. Here we go. One example for you. The transpose of previous matrix is written here. Now, if you apply elementary row operation, the very first row stays the same because the pivot is 1. Then you're going to apply elementary row operations. The second row becomes 0, 1, 9, negative 5, negative 6. The third row is now 0, 0, 1, negative 1, negative 1, and the final row becomes a 0 row. We are not interested in 0 row. Now take a look. You end up with 3 rows, 3 vectors. But recall that we write down the transpose of the matrix. So each one of these vectors can be converted into a column vector. So these 3 vectors, column vectors, form a basis for the column space. So as easy as that, write down the transpose of the matrix, then apply elementary row operations, and then count the number of non-zero rows. Write down their transpose, they become the column matrices or column vectors. In the next step, we want to find the basis for subspace. Suppose you have the space, and then we have a subspace spanned by these 3 vectors, negative 1, 2, 5, 3, 0, 3, 5, 1, 8. How do you find the basis for this subspace? First, you're going to create a matrix. Use V1, V2, V3 to form the rows of matrix A. Then write elementary row operation and convert it into row echelon form. Take a look. The very first vector is negative 1, 2, 5. It forms the very first row of your matrix. The second vector is 3, 0, 3, which forms the second row of the matrix. The third vector is 5, 1, 8, which forms the third row of your matrix. Now apply elementary row operations to convert this into row echelon form. It becomes 1, negative 2, negative 5, 0, 1, 3, 0, 0, 0. So basically have a 0 row, which we are not interested in. We're only interested in having non-zero vectors, non-zero rows. The non-zero row vectors of B are W1, W2, which are these 2 vectors. They form a basis for the row space of matrix A. That is, they form a basis for the subspace spanned by these 3 vectors. The next definition is the rank of the matrix. The dimension of the row space or column space of a matrix is called the rank of matrix A. It's denoted by rank of A. Well, to find the rank of a matrix, we convert it into a row echelon form by applying elementary row operations. Take a look. You have this matrix, and then your job, your goal is to convert it into row echelon form. It is going to be 1, negative 2, 0, 1, 0, 1, 1, and negative 1, and then you have 0, 0, 1, and 3 as the third row. The matrix B has 3 non-zero rows. What's the meaning of that? It means that the rank of the matrix is 3. Now that we learned about rank, we're going to introduce the null space or nullity of matrix A. Theorem says solutions of a homogeneous system, which we define below, n of A, all x values such that AX is equal to 0 is called the null space of matrix A. If A is an m by n matrix, then the set of all solutions of homogeneous system of linear equations AX equal to 0 forms a subspace of n space, and it is called the null space of matrix A. It's denoted by n of A, again, the set of all vectors like x such that AX is equal to 0. Now that you have a subspace, you're interested in finding the dimension of that subspace. The dimension of the null space of A is called the nullity of A. Let's take a look at the short proof. The size of A is m by n. So we know that x has size n by 1. When we are doing the multiplication, on the right-hand side, it's equal to 0. The constant terms are all 0. And the set of all solutions of the system is a subset of n space. This set definitely is non-empty. Why is that? Because the 0 vector satisfies the equation A times 0 is 0, and on the right-hand side, you have 0 vector. We can easily verify that it's closed under addition and also scalar multiplication. Suppose you have 2 vectors that are solutions of AX equal to 0. So it means that AX1 is equal to 0, AX2 is equal to 0. If I add these together, A multiplied by X1 plus X2, reminding the definition of multiplication, is equal to AX1 plus AX2, but this is equal to 0 and this is equal to 0. The summation becomes 0. So it means that X1 plus X2 also belong to the null space. Now for scalar multiplication, A times C times X1 can be written as C times AX1, which is C times 0 or 0. This is a scalar multiplication. So it just showed that both the addition and scalar multiplication are solutions of AX equal to 0, or in other words, they both belongs to this set. So we can conclude that the set of all solutions form a subspace of n space. So let us see an application here. How do we use this? Find the null space of the following matrix. You have this 2 by 2 matrix. To find the null space, we basically need to form a homogeneous equation, AX equal to 0. But before doing that, we can reduce this matrix into simpler form. Here you have 2, divide the first row by 2, and the first entry becomes 1, and the second entry becomes -1/2. If I multiply the first row by 3 and add it to the second row, it becomes 0 and 0. Why I did that? Because it helps me to solve the system a little bit easier. X1 plus -1/2 X2 is equal to 0. So solving the system, AX equal to 0 yields the following solution by setting X1 equals to T and X2 becomes 2T, and T is any real value. What's the meaning of that? It means that the dimension of the solution space is 1, and the basis is the vector 1 and 2. That's how we found the null space of the matrix. Again, remember the definition. We're looking for all x values. These are in the form of a vector in the n space such that ax becomes 0. Another example for you. You have this matrix now. We want to find the null space of the matrix. The null space of A is the solution space of the homogeneous system AX equal to 0. To solve this system, you can write the augmented matrix as we did in previous example. In reduced echelon form, however, the last column is just basically 0. It doesn't change anything. So you can basically take A and write it in row echelon form. This becomes 1, 2, 0, 3, 0, 0, 1, 1, and you end up with a 0 row. Now, the system 1 times x1 plus 2 times x2 plus 0 times x3 plus 3 times x4 is equal to 0. And from the second row, 0x1 plus 0x2 plus 1x3 plus 1x4 is equal to 0. And this is just 0 row. We need to introduce some free variables, like we can take x4 equals to t, and x3 becomes a negative t. If I plug in t here, my x3 becomes negative t. For the first equation, we have x4, which is t, but we need to introduce a new parameter for x2. So let us call it s. Then x1 can be written in terms of s and t. But what's the meaning of that? This means that the solution space of AX equal to 0 consists of all solution vectors of the form. We can replace x1 by negative 2s minus 3t. x2 is s, x3 is negative t, and x4 is t. Well, it basically forms two vectors that are multiplied by s and t. S times negative 2, 1, 0, 0, plus t times negative 3, 0, negative 1, and 1. What's the meaning of that? It means that a basis for the null space of matrix A consists of two vectors, the very first vector and the second vector. In other words, these two vectors are solutions of AX equal to 0 and all linear combinations.